Welcome back to the Mechanics of Solids lecture series. We're working on examples of torsion in indeterminate shafts and thin-walled tubes. Proceed with another example related to a thin-walled tube. This is a problem from Mechanics of Materials by Timothy Philpott, Wiley 3rd edition. The problem reads, a 24-inch wide by 0.1-inch thick by 100-inch long steel sheet is to be formed into a hollow section by bending through 360 degrees and welding the long edges together. Okay, so let's go ahead and draw a picture of this. Basically what it's telling us, we have a 100-inch long sheet, like so. The long dimension being 100 inches. The shorter dimension in this direction being 24 inches, and the overall thickness being 0.1 inches. And basically what we're going to do is wrap this around like this and weld the two seams on the edges together to give a tube section. Assuming a cross-sectional medial length of 24 inches, if the maximum shear stress must be limited to 12 ksi, determine the maximum torque that can be carried by the hollow section if and various shapes are indicated. The solution procedure would be similar for all of them. For us, let's go ahead and just solve part B, considering the shape of the section to be an equilateral triangle. Okay, so we are to find, in this case, the torque that can be applied for tau equal to 12 ksi, and knowing that the section is welded into a triangle. Remember, our equation for the approximate shear stress in a thin-walled tube section is equal to the torque divided by 2 times A sub m times T, the thickness of the section, where A sub m is the area to the midline of the section. Since this section is so thin, we don't need to worry about that too much, but the dimensions that were given in the problem we can assume to be the midline dimensions. We can rearrange this to solve for the torque. Torque is equal to tau times 2 A sub m times T. Our working units here, given units in kips and inches, we're going to solve for torque in kip inches, and our working units are, as mentioned before, kips, inches, and KSI for stresses. Okay? So we need to find this, in order to solve this problem, we need to find this area to the midline, A sub m, for a triangle section. Let's draw some sketches of what our triangle would look like. It's an equilateral triangle, meaning that every edge has the same dimension. Let's call that edge dimension D. We know that the perimeter of the triangle should be equal to the short distance of our sheet, which is going to be folded and welded. A perimeter for an equilateral triangle is equal to 3D. Set that equal to 24 inches, and we can quickly deduce that D is equal to 8 inches. So to find the area of that triangle, we need 1/2 times the base dimension, which is D, times the height. And because this is a 60-30-90 triangle, we know that that intermediate height is equal to √3 over 2 times the edge distance. So √3 over 2 times D will give us the area of the triangle. Simplifies to √3 over 4 times d squared, which was 8 inches squared, and that gives us an area of 27.7 inches squared. Now I believe I have everything I need to solve for the torque. Maximum torque that can be applied equal to tau. Our limiting value for tau is 12 ksi times 2 times a sub m, which we just found to be 27.7 inches squared, and times the thickness, which was given as 0.1 inches. SI and inches squared cancels out here. We're left with units of kip inches, which is what we expect. T max equals 66.5 kip inches. A sanity check. Number seems reasonable. For a torque in a thin section, the units check out, and we don't have any reason to believe that we've made an error.